Hello, in this video, I'm going to show you how to solve this problem involving a tether ball. So we have a ball of mass m. It's on a tether of length L, and it's swinging around at angular velocity omega. The first thing we want to do is draw a free body diagram. So I'm going to draw a dot. I have a gravity force downward, mg, and I have a tension up at an angle, T. And that's it. Those are the only forces. Okay, so the second part is we are given this angle, theta, and we want to solve for the angular velocity, omega. First thing I'm going to do is I'm going to apply F equals ma. That is, I'm going to write the sum of forces in the x direction and sum of forces in the y direction. In order to do that, I need to define an x and y direction. So I'm going to define x to be over and y to be up. Okay, so let's do sum of forces in the y direction first. So if we do the sum of forces on the ball in the y direction, we have a component of the tension. So let's break the tension into its components. So this would be T. This is theta. So this would be T cosine of theta, and that would be T sine theta. So putting those together, or well, we have, for the y part, we have T cosine of theta, and we have a minus mg. And it's not going up or down, it's going around in a circle, so the acceleration in the y direction is 0. So we set that equal to ma, which is 0. Okay, now we'll do sum of forces in the x direction. So we have minus T sine theta, but it's being pulled in the minus x direction. And it's the only force in the x direction, so we're just going to have set that equal to mass times acceleration in the x direction. So we see that our we get to that. Okay, so this is this acceleration here. This is our centripetal acceleration, AC, right? Because that's what keeps it going around the circle. We are told that well, we know what the magnitude of centripetal acceleration is omega squared r. Because I only know the magnitude of the acceleration, I'm going to drop this negative sign here, and I'm just going to have T sine, T sine theta. T sine theta is equal to m omega squared r. Okay, it's working out so far. So I know, so I plugged that in there. Okay, let's see. Let's remember what we were getting. We were trying to get omega. So we're trying to solve for omega. We're not given tension, and we're not given r. So we're going to have to find tension in r. Okay, well, we can get tension from this equation up here. We use that equation. We can solve for tension, and we get we would get 10 if we take that equation. I would get tension is equal to mg over cosine theta. I can then plug that in over there, and I would get mg over cosine theta sine theta is equal to m omega squared r. Okay, so we eliminated one of our unknowns. We eliminated t, but we still have omega, which we don't know if we're trying to find, and r, which isn't given. Okay, so let's go back and look at our picture, how do we get r? So the radius of that you're referring to when you talk about centripetal acceleration, omega squared r, is the radius of the circle that the object goes in. It is not the length of the string. We can just find r from geometry. There's a angle there, and we can see that r is equal to L sine theta. R is equal to L sine theta, just from geometry. We plug that into there, and we get mg over cosine theta sine theta is equal to m omega squared sine theta. We can cancel our sine thetas. We can cancel our m's, and we can take a square root, and we get omega is equal to the, oh, whoops, I missed an L. When I stuck that in, the R in, it needed to be L sine theta. So now I can cancel my sine thetas and divide by L. I get G over L cosine theta square root. And that is the answer. Okay, the last question is, does the answer increase with increasing m, decrease or with increasing m, or not depend on m? And you can see there's no m's in this equation, so it does not depend on m. Why? Well, basically, we saw what happened right here in this last step. The m's canceled. The m is doing two things. Gravity is pulling down m, and m is being pulled out by centrifugal force, if you want to think about it that way. And those sort of cancel each other out. Another way I like to think about this is, suppose we had two tether balls. So we had two ropes, two tether balls. They're just like just right next to each other. They're swinging around together. So if they're identical, they'd swing around, same omega, have the same angle. If we suddenly tied them together with a piece of dental floss, that wouldn't change the situation noticeably, but it would double the mass of the effective ball. So by changing the mass, we didn't change anything. So clearly a mass cannot change the answer. So no, basically. Okay, and that's how you solve that problem.